queries, call us at +1 678 648 4277. You can mail us at info@architectureassignmenthelp.com or reach us at https://www.architectureassignmenthelp.com. Problem 1. This question deals with the 6-instruction ISA that was discussed in Lecture 02 and Lecture 03. As you saw in Lecture 02 and Lecture 03, the instruction encodings for the 6-instruction processor are as shown in the table below. Instruction opcode 16-bit encoding function. MOVRA D0000 opcode, 4 bits, destination register, 4 bits. Address 8 bits, RF, A, M, D. MOVD, RA0001 opcode, 4 bits, source register, 4 bits, address 8 bits, M, D, RF, A. Add 0010 opcode destination source RF, A, RF, B, RA, RB, RC0010 opcode, 4 bits, destination register source register, 4 bits. Source register, 4 bits. Source register, 4 bits. RF, A, RF, B, plus RF, C. MOVRA, hashtag C0011 opcode, 4 bits, destination register, 4 bits, constant, 8 bits, RF, A, C. Sub RA, RB, RC0100 opcode, 4 bits, destination register, 4 bits, source register, 4 bits. Source register, 4 bits. RF, A, RF, B, RF, C. Jumps RA, X0101 opcode, 4 bits, source register, 4 bits, offset, 8 bits, if RF, A, == 0, PCPC plus offset. ArchitectureAssignmentHelp.com. Question A. If RF, A, == 0, PCPC plus offset, assume that you want to augment this ISA to support 20 additional and unique instructions, e.g. multiple, and, or, etc., while still keeping the instruction encoding as 16 bits. How will the execution and encoding of the add instruction be affected? Other instructions could be affected too, but you just need to comment on how the add instruction will be impacted. Answer: the number of bits dedicated to the opcode will need to increase from 4 to 5. As such, there will be one less bit to encode the number of the destination register or the number of one of the source registers. Given this change, an extra bit will be needed to specify the opcode. The result of the add must be written to registers 0 through 7, or one of the source registers will only be allowed to be register 0 through 7. Question B. Now, assume that the 20 new instructions have all been added. Their addition has resulted in changes to the state diagram discussed in lecture. A portion of the new finite state diagram is shown below. Given this new state diagram, how many clock cycles will the code, that is also shown below, take to run? Code MOVR1, number 1 MOVR2, number 2 MOVR4, number 4 sub R5, R4, R2 sub R5, R5, R2. ArchitectureAssignmentHelp.com. Jumps R5, X add R1, R1, R1X, add R1, R2, R4 MOV10, R1. Answer: MOVR1, number 1 hashtag R11, for CC's MOVR2, number 2 hashtag R22, for CC's MOVR4, number 4 hashtag R44, for CC's sub R5, R4, R2 hashtag R5 R4, R2 = 23 CC's sub R5, R5, R2 hashtag R5 R5, R2 = 03 CC's jumps R5, X hashtag jump to X3 CC's add R1, R1, R1 hashtag skip X, add R1, R2, R4 hashtag R1 R2 plus R4 = 63 CC's MOV10, R1 hashtag M, 10, R1 4 CC's. Underscore 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 total, 28 CC's. ArchitectureAssignmentHelp.com. Question C. In what clock cycles does R1 change state? I.e., when is new data put into R1 available? Answer. R1 changes state after the instruction add R1, R2, R4 is executed. This is in cycle 24, which means that R1 data is available at the beginning of clock cycle 25. It also changes state in CC number 5. Comments. The most common mistakes I observed had to do with parts B and C. If a mistake was made on part B, it generally had to do with the fact that you either assumed that both add instructions were executed, or miscounted the cycles from the state diagram. If a mistake was made on part C, you generally assumed that data was available in the last cycle of execution, not the next cycle. This is why the comment, when is data put into R1 available, was included. ArchitectureAssignmentHelp.com. Problem 2. Question A. Consider a hypothetical branch if equal instruction that is 32 bits long, minus 6 bits are used to encode the opcode, 6 bits are used to encode one register number, 6 bits are used to encode another register number, minus 14 bits are used to encode an offset that will be added to the program counter, PC, if the branch ends up being taken, and a new instruction address is required. Oh, the number is not in 2's complement form, and all 14 bits can encode a constant. Thus, the instruction syntax might be, BEC R12, R11 X. If R12 equals R11, the PC will be set to PC plus X instead of PC plus 4. Given this instruction, is the code shown in the table below valid? Why or why not? Address instruction. 5000. 5004 BEQ R12, R11 X. 5008 add R1, R2, R3. X, 21256 sub R1, R2, R3. ArchitectureAssignmentHelp.com. Answer, yes. This code is valid. The 14-bit offset allows you to encode a number that is as large as 214 to 1, equals 16,383. Thus, even if the PC has not yet been increment, you can reach address 21,384, 5004 plus 16383, which is beyond address 21256. Comments. Most students got this question right. Question B. Assuming that the PC has already been incremented by 4 when the comparison for the BEQ instruction at address 5004 is made, how many instructions away from the BEQ instruction could we reach? Answer, floor, 214 to 1, / 22 equals 4095 plus 1 is equal to 4096. The floor function is needed because the address must be a multiple of 4. Comments. Some assumed that the PC was not increment and based their answer accordingly. This received full credit as long as your answer was explained correctly. Question C. Assumed that you have 24-bit instructions. A hypothetical R-type/ALU instruction, i.e. add, subtract, multiply, etc., might be encoded as follows: opcode destination and source register. Source register function code. 6 bits, 6 bits, 6 bits, 6 bits. ArchitectureAssignmentHelp.com. Thus, one register serves as both a source and a destination, add R5, R7 #R5 R5 plus R7 6 bits. Given this type of encoding, i.e. where one register is always both a source and a destination, can the code shown below be translated into assembly with just these types of ALU instructions? If yes, write your code. If no, explain what functionality is missing. Y equals Y plus X, Z equals Z asterisk Q, Q equals Y plus Z, Z equals Z asterisk Y. Answer, yes. It is possible to come up with a sequence of instructions given the specific code shown below such that the operation is in fact possible. For example, Y equals Y plus X, Z equals Z asterisk Y.